So we are at the last leg of the transmission line. So I'm going to take up two topics. One is the idea of Smith charts, right? So we are not going to go too much into detail, but there is always a curiosity for anyone who takes up microwave design and modeling for high frequency circuits, that you often see this Smith chart used in presentations or even in publications. So at least to dispel the fear of having not knowing what the Smith chart is all about, I'll just give you the basics. But these days Smith charts are mostly used as a visualization tool, right? So think of it as, say, sometimes even in rectangular plots, right? So instead of plotting x versus y, where x and y denote some quantities, and plotting y as a function of x, sometimes people might ask you to make the x-axis or the y-axis logarithmic, right, in order to be able to see several orders of magnitude. So just like that, right? So just a visual aid or a visual tool that is able to simplify and give us some views of what might be going on in the circuit. Okay. So Smith chart is essentially a mapping. Okay. Fundamentally is simply a mapping between one complex plane to another complex plane. Okay. So there's nothing to worry about. The chart, of course, looks very unconventional, right? So I'm going to show that very briefly towards the end of this discussion. But remember that our loads, right, that are connected to the transmission line are generally a complex number, right? So it can be represented in the complex plane using just two variables, right? So I'm going to take a point z prime z bar, which is x plus iy. Okay, and then I'm going to map this to another point in the gamma plane. Right, so gamma is, say, u plus iv, right, and the function that takes me from the z plane to the gamma plane is essentially the function that we saw for the reflection coefficient, right. So I'm just going to say f of z is z minus 1 by z plus 1. Okay, so here I'm essentially looking at the normalized form, right. So remember that gamma was written as ZL minus Z0 by ZL plus Z0. Now if I divide the numerator and denominator by Z0, I'll get the normalized impedance, right. So a form similar to this. The reason to do this is so the chart is independent of the characteristic impedance, right. So we know that automatically that if you are showing me a Smith chart in the gamma plane, that you have normalized all the impedances to the characteristic impedance of the transmission line, the lossless transmission line, right. So the Smith chart essentially forms a map of all physical loads, right. It could be a combination of inductors, capacitors, resistors, whatever it be, linear loads, right. It is mapping that to the gamma plane. Okay. So what is special about this function here is that it is invertible. All it means to say is it's a one-to-one map, right. Every point in the gamma plane has a corresponding point in the z plane, right. And there are many terms or names for this. You might hear in mathematics that this is called a linear fractional transformation, or a Mobius transformation. So of course mathematicians have explored these maps very extensively. We don't need to go too deep into that. We just need to understand for our specific case in electrical engineering, what do these maps tend to do, right? So this analytic function f of z is a conformal mapping that essentially maps. So in the z plane, if I have constant x contours or constant y, okay. So the analytic function f of z essentially maps lines of constant x and constant y in the z plane to circles, right? So we'll take a quick look at that. But what I'm trying to say is, I introduced a word conformal mapping. Conformal mapping just indicates that it preserves the angles, right? So it preserves the angles that these lines of constant x or constant y make. So if I take constant x or constant y lines, they would intersect at 90 degrees, right? So if I map these lines to the gamma plane, there would be some circles, right? And these circles would in general intersect each other, preserving the angles at the intersection, right? What I mean by that is, if I were to take some colors here, let's say if I have, these are lines of constant x, right? And say these are lines of constant y and they intersect at right angles. The mapping would essentially map them to circles such that if you look at the intersections, they will still preserve the same 90 degrees, right? So these are some observations that we can conclude. Okay, so let us look at this analytic function and make some basic calls, right? So remember that modulus of gamma is always between 0 and 1. Okay, you take any load, right, or any z prime, the gamma value is always, modulus of gamma is between 0 and 1, right. So it is essentially saying that the entire right half plane, right, remember that x being negative denotes negative resistances. We are not looking at that, right. So resistances have positive values, positive real values, and y, the imaginary part which comes from inductors and capacitors, can be positive or negative, right. So but strictly all loads, all real loads will be in the right half plane of the z plane, right, or the complex load plane. This maps entirely to a circle, right. Remember, modulus of gamma being strictly less than 1 indicates a circle of unit radius, right. Okay, so in the gamma plane, if I say that modulus of gamma will never ever exceed the value of 1, then it's essentially a circle centered at the origin with a radius of 1 unit, right. So, this is to say that all practical loads or real loads are mapped from the right half plane to within a circle of radius 1, right. And there is also another interesting property, which is this mapping has two fixed points. Okay. What I mean by that is, if I set f of z equals z, right, so the value in the z plane as well as the value in the gamma plane is the same, right. Then I essentially get two solutions, and they happen to be plus j and minus j. Okay, so these are the two fixed points of this transformation, but all other values will map correspondingly according to this. But remember, all of the points in the right half plane have to find themselves a point within the unit circle in the gamma plane, right. So, we are looking at the yellow shaded region in the z plane mapping to the yellow shaded region within the unit circle in the gamma plane, right. So, this is the transformation that I am making when I say that I am trying to plot a Smith chart, right. So, all the loads that I have, that I am conveniently trying to map them to the reflection coefficient that it will have, right, with respect to a characteristic line impedance, right. So, I take the impedance, normalize it to the characteristic impedance, and if I want to find out what reflection coefficient that particular load will have, then I just look at the gamma plane and look at the gamma value to get the complex gamma value directly. And I can also, since the mapping is 1 to 1, every point within this unit circle corresponds to a very unique load, right, a combination of R, L or C to give me that particular reflection coefficient. Okay. So, I will quickly try to show you how the Smith chart evolves. So, we are looking at resistances, right. So, let us say I have an R plus Jx. Remember, this R and X are normalized to the characteristic impedance of the transmission line, right. So, if I were to take a couple of lines and see how these lines transform. So, let us say this is R equals 1 and we have R equals 2, right. We can also look at R equals 0 for sure, right. So, we have no resistance, just a complex an imaginary impedance, just say a pure inductor or a capacitor. We will see what that maps to, right. So, in the gamma plane, the R equals 0 essentially maps to a unit circle. That is a terrible circle. Okay. Because remember, in the case of discussion on power transfer, we said that if I have Jx minus 1 by Jx plus 1, remember this is just a complex conjugate, right. So, regardless of what the value of x is, modulus of gamma is going to be 1, right. So, we can say that the R equals 0 maps to the unit circle. Okay. So, R equals 0. Okay. So if we say even x is 0, which point is that? That is essentially a short circuit, right? So r equals 0, x equals 0 is essentially a short circuit, and that essentially maps to -1, right? So if you put x equals 0 in this expression, you will notice that the reflection coefficient is -1 for a short. So this is -1, right? So this point here specifically maps to this point. Okay. Now we'll take a look at r equals 1, right? So what does r equals 1 do? So remember, r equals 1 and x equals 0 is the perfectly matched condition, right? So you have matched the load impedance to the characteristic impedance of the transmission line, in which case the reflection coefficient is 0, right? So when x equals 0 and r equals 1, which is the intersection of this vertical green dotted line with the x-axis, that point will actually correspond to a reflection coefficient of 0, or the center of this, right? So you can check, be using a computer, but essentially that line, the green dotted line, will map to a circle that is centered at half and has a radius of half, such that it passes through the origin, right? So we have an r equals 1, right? So remember that the resistance is constant along the dotted green line, right? So I am keeping the resistance constant and only changing the imaginary part, right, which is the value of the inductor or capacitor attached. And if whatever I do with the value of inductance or capacitance, I will always lie along this green dotted circle in the gamma plane. Okay, so this is the load plane and this is the gamma plane. Okay, and if I look at r equals 2, it will essentially form smaller and smaller circles for larger and larger values of r, right? Okay, so this is sort of the mapping that's happening, right, for constant resistance, right? So you will notice that there are lines in the Smith chart. First of all, the Smith chart is going to be a circle with unit radius, right? And then all other denominations for resistances and inductances will be in the form of circles, right, or segments of circles that indicate the different resistance, constant resistance lines or constant impedance, imaginary value lines. Okay, so we will also quickly do the mapping. So in this case, x equals 1, let's say x equals 2. You can see that I am only interested in the right half plane, right? So x can be both positive or negative. And we will see how these map to the gamma plane. So again, the range that we expect to see all the gamma values is within the unit circle. Of course, there is x equals 0, right, and for all resistances, that essentially maps to this line, right. So from here to here. So the entire positive real axis is mapped between -1 and 1, right. We have projected all the values along the x axis to values between -1 and 1. But the x equals 1 is actually a portion of a circle that look like these. They are also part of a bigger circle, but because we know that we are only looking at the right half plane, these circles are truncated. Okay, so you can correspondingly look at the constant x lines, right, in the z plane or the impedance plane, and they happen to be these truncated circle segments in the gamma plane. Okay, so with that information in mind, this is how a traditional Smith chart looks like, right. So the reason I wanted to show this to you, that you can normally see these charts and you see curves drawn on them, right. So when you have an inductor or a capacitor, obviously the impedance of these inductors and capacitors are a function of frequency. So you can actually plot impedances as a function of frequency on this Smith chart, right. So remember that this is my gamma equals 0 point. Okay, so the radius of this circle is 1. Okay, so this is my short circuit. This is where R and X is 0, right, resistance and the imaginary value of impedance. So this point is essentially the open circuit, right, and remember the north and south were the fixed points, right. And so basically if I have an intersection, right, so remember these lines that are being drawn, right, are essentially lines that have constant values of x, right. So the ones that I have marked with the tick, they are essentially lines that will look perfectly straight in the z plane, right. So they have constant x values or imaginary parts of the impedance, and these circles that you see, not quite concentric but reducing in radius, those are all constant resistance circles, right. So vertical lines in the z plane map to these circles, and the radius of these circles tell you what is the resistance, right. So you have lower resistances. So I would say this segment resistance is lower than the impedance, right, and to the right of gamma equals 0 point, there are resistances that are higher than Z0, right. So you can see that for resistances higher than Z0, the reflection coefficient will be positive, right. So gamma is greater than 0. Resistance is lower than Z0, gamma will be less than 0, right. And another thing is, remember that gamma as a function of L was essentially gamma at the load multiplied by e to the minus 2j beta L, right. So So remember that e to the minus 2j beta L is simply a complex number of unit magnitude and has some phase to it, right? Which means that the modulus of gamma L taken at any point along the lossless transmission line is the same, right? So essentially the meaning of moving away from the load and towards the generator on a lossless transmission line amounts to going on a circle of given radius mod gamma L, right, and you are just incrementing in phase, right. So for positive L direction you will essentially be so let's say I have a load of some r plus jx and then I go, of course this will right. So this is say some gamma L, right. So as I go along the transmission line, the lossless transmission line, I'll essentially go along this circle, right, because the modulus of the reflection coefficient is the same. I'm just adding some phase to it, right. So these are also called constant VSWR circles, right. So for all loads that are on this blue circle, you will have the same voltage standing wave ratio. Why? Because rho just depends on which was V max by V min, simply depends on the modulus of gamma L, right. So rho will be constant for all gamma L's that have the same absolute value, right. Even if there is a phase difference, the rho will stay the same, right. So these are constant VSWR circles. It is another way to say it is all the loads that lie, right, the R plus Jx corresponding to the dots on this blue circle will all have the same voltage standing wave ratio, right, or you can say that they have the same modulus of the reflection coefficient, right. And actually when you do the transformation going from the load towards the generator for positive L, you are essentially going clockwise, right. So that is the reason for that L being switched, right. So remember we had X and then we substituted that as minus L. We are used to conventions like the clock hand which goes clockwise, right. So conveniently the clockwise motion here corresponds to us going to positive L's, right, or towards the generator away from the load. Okay. So I think that this understanding of Smith charts is sufficient for you to be able to at least interact with these Smith charts when you see them either while reading journal papers or you see presentations or online webinars. You should have some notion that Smith chart is essentially a map of all the complex loads that we might see in a different plane, right, in the gamma plane. And there are some well-known established mapping points that we can remember, right, like the short circuit, the open circuit, the matched point, right. And we also understand the axes, right. So remember that these lines are like the axes, right? So just like we have grids in the rectangular plot, so these grids looks like circles instead of having to be perfect vertical or horizontal lines. In the Smith chart, these lines look circular, right, or portions or segments of a circle. So there's nothing to worry about in terms of being daunted about the looks of a Smith chart. It is but a simple transformation that helps us visualize data. Mainly, I would say the convenience is, for example, open circuits or infinite loads is something that we are able to realize that very easily, right? So I just have a floating or an open transmission line, but to be able to denote that on a plot, right, is very difficult because the point infinity is very hard to draw. But doing this transformation allows us to be able to look at any load that you might have, right? Because they all condense, all the points in the right half plane condense into points within this unit circle. So it is very convenient for us to study all loads in a single plot.